So hello, today we're going to do example problems for chapter 5. Hopefully this will help a bit moving forward for the homework and future exams, since, that's a thing also. I've often said which ones are old exam problems. Question 1 is an old exam problem. Oh, sorry, question 1 is not. Question 1 is too simple. Question 2 is an old exam problem, though it's a little simpler than something I normally put. It was kind of weird I put this on. Question 3 and question 4 are both old exam problems. Um, in general, we haven't quite finished energy yet, even though we finished the chapter. We're going to revisit energy in chapter 8. And so any problem I put in an exam about conservation of energy might also include a topic we haven't covered yet, which is kind of a weird fact. So I'm only looking at the types of problems that do include this, hence that 3 and 4 are really the old exam problems you might see. But I'm going to start with question 1. And in general, before I start with anything, conservation of energy is based off a decently simple idea. And that is, as long as you have conservative forces, initial energy equals final energy. Well, energy is a sum of kinetic energy and potential energy. Kinetic energy is energy of movement, and potential energy has two terms. There's potential energy due to gravity and potential energy due to springs. So this first problem, undo, which I just drew a picture of in Zoom, is as follows. A pole vaulting running at 10 meters per second vaults over a ball. Her speed when she is above the ball is 1 meters per second. Neglecting air resistance as well as energy absorbed from the pole, determine her altitude as she crosses the ball. Now, it doesn't seem like you should be able to figure this out. She's running and jumping, but we know the velocity down here. Velocity down here is 10 meters per second. And I know the velocity here. The velocity here is at 1 meter per second. But what I have is someone changing height. That if I call my two spots A and B, and I'm just kind of matching the A and B with my VA, VB, but really it's going to be, this is my A, this is my B. I can say at A, I have a velocity, and my height is 0. Because I'm on the ground, I'm going to make that my lowest point. At B, I have some velocity, and my height isn't 0. And at all points, I can say I can solve for the energy. And that's simply how you do conservation energy problems. You're going to write an equation for the energy at all points. Well, energy is the sum of kinetic energy plus potential energy, or 1/2 mv squared plus mgy plus 1/2 kx squared. The thing is that 1/2 kx squared only comes up if there's a spring. And there's no spring here. Since there's no spring, I'm not going to include it. And I'm going to say that my energy at A is just 1/2 mva squared plus mgy of A, but that's 0. My energy at B is 1/2 mvb squared plus mgy of B. And since conservation of energy says E initial, or EA, equals E final, or EB, I can say 1/2 mva squared equals 1/2 mvb squared plus mgy. Once I get to that point, it's all algebra. I would divide both sides by m. Well, actually, no, I'm solving for this right here. So I'll subtract 1/2 mvb squared from both sides. I can divide both sides by m, which will just cancel out all of my m's. I'm going to do something kind of interesting here. I'm going to factor out the half. This isn't required, but it's just going to make it look nicer. And then I can divide both sides by g. So I wrote 100 meters per second squared. I meant 10. I squared it already in my head. 10 squared is 100. That's the general idea. I just write an equation for the energy at A, I write an equation for the energy at B, and I say that they're equal to each other. Once you do that, you just rearrange and solve. And rearrange and solve however you need to get whatever you're looking for. Any questions, though? I'm guessing this makes some level of sense, then? Okay. This next problem, as I said before, this is an old exam problem. And it says, at the time I wrote this problem, so this is a few years back, the tallest roller coaster in the world was Kingda Ka. It's at Six Flags Great Adventure. I'm missing a letter. That should be Great Six Flags Great Adventure. Don't know how I never noticed that. In Jackson, New Jersey. It's actually pretty close to where I grew up. Random, weird, unimportant fact. So this roller coaster, like most roller coasters, you're gonna go like tick, 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 tick up the hill, and then you go down by gravity. This one does something else. Using hydraulics, you sit there and it shoots you out, and you go rocketing up the hill solely by having so much velocity at the bottom, and then you just make it over the hill, and then you go around by gravity like you would normally with a roller coaster. But yeah, you get rocketed up just because you're going so fast at the bottom. And what it is you start, and I'm going to draw this roller coaster flat. I'm eventually going to talk about this whole thing, but just drawing it, and I'll draw it on the screen. That'll be easier. Is you start at some height and you go up over a real high bit, and then down, and then over a second hump, and then eventually you come back to where it starts. You got to see that this is the goes up, big hump, down, second hump. So when you start at some height and you go up 127 meters. Now that's saying from that initial spot. And so I'm saying that this point right here, which I'm going to call B, and I'm going to call where we started A. I'm going to get a little ahead of myself, but eventually I'm going to talk about at the top of this hump. So I'm just going to preemptively call it C right now. I say that there's 127 meters up from where you started. So let's just define my initial height as 0. And then I can say my height at B is at 127 meters. And it says you go over the top at the slow speed of 0.4 meters per second before descending back down while spiraling. That means when I go over that point B, my velocity at B is 0.4 meters per second. And my question is, what is the velocity needed at the bottom to get you up and over the top? AKA, what's the velocity at A? Well, I'm going to solve this with the same logic. I'm going to say that my energy at A equals my energy at B. Well, my energy is kinetic plus potential. Plus potential due to a spring, but there's still no springs here. And since there's no springs, I'm going to ignore that. Now at A, my height is 0, just like in the last problem. And so just like the last problem, we say my energy at A is 1/2 mVA squared. My energy at B is going to be 1/2 mVB squared plus mgyb. And I'll use conservation of energy and set these two equal to each other. Now this time I'm solving for VA. So what I'm going to do is I'm going to divide everything by m. multiply everything by 2. Which this might look familiar because it's a kinematic equation. And I just plugged in my numbers here. 0.4 meters per second squared plus 2 times 9.81 meters per second squared times 127 meters to get 249.9, and I can square root. And you get 49.9 meters per second, which is pretty goddamn fast. Any questions so far? So another light. Pope B says, what is the velocity when the roller coaster goes over the second hump? And then they say is at a height of 47.5 meters. That's a horrible question, Mark. Well, here's the thing. At that second hump, all of these equations still hold true. What I would say is I have a new equation for energy, where the energy at C is 1/2 mvc squared plus mgyc. Because I would just say at that height, we have some new height, new velocity. And just like before, I'll set them equal. I could set this equal to here. I could say EB equals EC, or I could see EA equals EC. It doesn't matter which one I do. Now, I'm going to say EA equals EC just because EB has more terms. Because it has more terms, it's more complicated. When in doubt, use the simpler term. If you use the simpler term, you're less likely to make a math error. Now I'm solving for VC. So I'll subtract mgyc from both sides. Divide both sides by m. Anytime you don't have springs, if there's a conservation of energy and there are no springs, you always are going to be able to get rid of m's. M's will only be needed for problems with springs. I'll multiply both sides by 2. And I can solve. Am I still on the screen? Barely. VA, what was VA? 49.9. And so VC is then the square root of this. I'm not going to bother writing that out. And I can get a value. Questions?
Yeah, I'm just confused as to why the equations for A, B, and C are all different or similar but different.
Well, B and C are identical. It's just I said one is B and one. I said one is V sub B, one is V sub C. A is really also the same equation. It's just that Y is 0 for A. And so this term for A, it's going to be mg times 0. And m times g times 0 is 0. So that last term just goes away because it's 0. Does that make sense?
Yep.
Okay. Any other questions? Okay. The next problem Now I'm going to start doing ones with springs. And 3 and 4 both will have springs. And as I said, these are both old exam problems. I often include springs on exams. I normally include springs or something rolling, and that something rolling is the thing that we haven't covered yet. And this says, in the Sonic the Hedgehog games, at least the old school ones, because I usually deny the acknowledge of newer ones, Sonic uses jump pads, which is just a big spring, to jump very high. Sonic, who, according to the web, has a mass of 35 kilograms, because of course Sonic's exact mass is a known quantity, can use a jump pad to get a maximum height of 15 meters above the spring's equilibrium position, after compressing the spring 0.1 meters below the spring's equilibrium position. What is the spring constant of the jump pad? And later on, what is the velocity when the spring passes through equilibrium? Okay. When doing these, and you know what? Shit, shit, I did not mean to do that. I was just trying to make that picture bigger, but instead I quit it by mistake. Give me a second. That'll be right back. Oh, I hit it. That's what I did. Okay. Okay. When you want, what I'm going to do is I'm going to use conservation of energy. I'm going to say that I have 3 locations, A, B, and C. And that the energy at A equals the energy at B equals the energy at C. And energy in general is 1/2 mv squared plus mgy, but now there's a spring. Because there's a spring, I need to add the energy of a spring, 1/2 kx squared. Now in this problem, I have x and y. And if you look at it, he's moving up and down. But so is the spring. The spring is moving up and down. And so I'm going to, for this case, so I'm using Mario instead of Sonic, which seems kind of sacrilegious for what I'm doing. But I'm saying that he's starting at some spot. The spring is compressed, that's A. B is right here when he's just going full velocity. And C is at the max height. Because if I just take this and push off, which is kind of weird to do it horizontally, he'll go flying up. And so since the spring is moving in the same direction as gravity, I am, for this problem, gonna just put a y here instead, because it's going up and down. And what I'm going to do is I'm just going to look at what my values are at each spot. See, at each spots A, B, and C, I have to say, what is the velocity at that point? And what is the height at that point? And I'm not going to write on the figure, I'm going to draw on the page. So I'm going to say at A. At A, that is the lowest point. They say he compresses a spring and is standing on it. If he's just standing on a compressed spring, he has no velocity. And they say that it is 0.1 meters below the equilibrium position. Now, in potential energy, we can make y 0 if we want for gravity. But for a spring, it's pretty set. 0 potential energy for a spring is the equilibrium position. That in this case, 0 is right here. That's 0, because the spring isn't compressed or retracted. If I was to pull this to get ready to fly in, that would be a value of y. And if I was to push this in, that would also be a value of y. But this has to be 0. And so if I compress it 0.1 meters, what that means is I'm going beneath the 0 point. If I'm beneath the 0 point, I have to say my height at A is negative 0.1 meters. Negative because I'm beneath. At B, and I'm actually going to shoot up at you guys, it's what I'm going from here to him flying up. At B, at this height, it is traveling through the equilibrium and launching. Well, if I try to do it sideways again, it's traveling from here, and it's when he's still moving upwards. And so at B, I have some velocity. But at B, that's when I'm right like this. I'm at my equilibrium for the spring, and I define that as my 0 for height. So my height is 0. At C, C is my highest point, and that's when he's in between going down, up, and going down. At my highest point, I always know my velocity is 0. And at C, I have some height. They say he goes 15 meters up. And what I'm going to do is I'm going to use these terms and plug it into this guy for A, B, and C. I'll say my energy at A is 1/2 mv squared, but v is 0, plus mgy plus 1/2 ky squared. My energy at B is 1/2 mv squared plus mgy, but y is 0. So y is 0, so I don't include it. Plus 1/2 ky squared, but y is 0, so I don't include it. My energy at C, v is 0, so this first term goes away. mgyc. But let's look at the spring. You see, you can really see it in the picture as opposed to me playing with this guy. When he goes up, that spring doesn't go up with him. The spring stays down on the ground. That if I take this toy, and it's really weird to do this sideways. When I take this toy and I have it shoot up, that once it shoots up, once it leaves, the spring still isn't stretched. That it could, it's extra weird to be at a different angle. Okay. That right here it's compressed, but once it goes up, it's not compressed. And no matter how high he goes, that stays not compressed or stretched, because once again, stretching would do the same thing. And so once I'm in the air, the spring isn't doing anything. And especially with my Sonic problem, where the spring isn't attached to him like this Mario toy that is ancient, is I can say that the spring isn't doing anything in C. It's just sitting there. And since the spring isn't doing anything in C, there'll be no spring pulse. And what I know is that my energy at A equals my energy at B equals my energy at C. So I have two things I want to solve for. Velocity at B.
Sorry, wait. So I see why we have no spring in C, but can you explain it again for B?
B, because that's at the 0 point. It's when it's why the spring isn't stretched or compressed.
Okay.
It's at the equilibrium position. Now, part A said find K. K only shows up in EA. So I'm going to use my energy at A. And I'm going to set that equal to either my energy at B or my energy at C. But B has a question mark in it. So let's use C. That mgya plus 1/2 kya squared equals mgyc. So if I want to solve for k, at this point I'm going to stop color coding. I'll subtract this term from both sides. I don't have to do this bit, but I can factor out an mg, which I just like doing because I think it makes it less messy. I can then multiply both sides by 2. And divide both sides by ya squared. And plug in 2 times his mass, 35 kilograms, times g, times y of c, 15 meters, minus a negative 0.1 meter over a negative 0.1 meter squared. Common mistake here when doing this problem is people, when squaring negative 0.1 meters squared, getting a negative answer. Keep in mind when you square a negative, it becomes positive. And you get a really fucking huge spring constant, which I don't think is that surprising because we're trying to launch someone 15 meters up. Video game logic is normally not very sound physics logic. Any questions? So part B says, what's his velocity at B? If I want to get his velocity at B, I'm just going to set my energy at B equal to my energy somewhere else. And I can either set it equal to my energy at A, or I can set it equal to my energy at C. I'm going to use my energy at C because it's simpler. A has 2 terms, C has 1 term. It'll be less of a mess. And say 1/2 mvb squared equals mgyc. I'll divide both sides by m, multiply both sides by 2, and then square root both sides. This is very similar to the pogo stick problem I did. It's like a 50-50 chance that the first problem on your next exam will involve conservation of energy with a spring. It's going to be conservation of energy with a spring or rolling, which, as I said, we haven't covered yet. So, yeah, any questions? I'll do one more. And this next one is about the anime One Piece, which I am very behind in. I haven't watched in forever. In the anime One Piece, there was a character named Monkey D. Luffy. And he has the ability to do all sorts of weird shit, actually. But one of them is inflate like a balloon. And he's a pirate, and anytime a cannonball is shot at his pirate ship, he often inflates like a big balloon, has the ball hit him, and bounces it back. So let's say Monkey D. Luffy does this. An 8-kilogram cannonball is fired at Luffy while traveling at 150 meters per second, as shown in A. What that means is that A, there's a cannonball moving at 8 meters per second. Really, I should debatably argue that, 150 meters per second, that was its mass. I could argue negative because it's going to the left, but conservation of energy doesn't really give a shit about direction, so I'm going to ignore that fact. He stops the cannonball by having it hit him, pushing his stomach in. Treat his stomach as a spring with that spring constant. How far is his stomach compressed to stop the cannonball? So what that means is at B, it's not moving. And I say treat his stomach as a spring. How far in does that go? Now, if I look at A, his stomach wasn't compressed today. So I will have no compression at A. Part B is going to involve case C, and I'm just going to read it all out now. It says Luffy launches the cannonball at the attacking ship's mast, which is 30.4 meters upwards. What is the velocity of the cannon when it hits the mast? Here's the thing. The last problem, the spring and movement was in the same axis. This one, the spring is sideways. We have something coming. Put it up. I need something I can be flinging. I have so much random shit in my office, and I never. Okay. So I have the cannonball coming in, bouncing, getting compressed, and then being launched upwards like that. And so it's just going to be here when it's first coming in, here when it's compressed, and then, yeah, boo, launched upwards. What I can say is that at C, we have some velocity. But here, the spring is just going side to side. The potential energies I have to lose, that's a separate thing. That the axis of the spring being compressed is not the same as the height. And so I'm going to have to separate out compression of spring in X and height in Y. Where I say initially in A and in B, I'm at the same height. I know that because it says assume no change in height. So I'm just going to make that my 0 point. In C, I've gone upwards 30.4 meters. But at C, take a look at the drawing. His stomach isn't doing anything. We're not compressing in. And so at C, we have no X. That, yes, the cannonball might have moved in X, but we don't give a shit about the cannonball's movement in X. What we care about is the spring's compression. That we have A, B, C. And in both A and C, this spring is not compressed. It's only in B that the spring is compressed. This Mario toy is stuck on there we go. And we can say that the energy everywhere is going to be kinetic plus potential. And now I'm going to keep Y and X separate. We can also say that our energy at A equals our energy at B equals our energy at C. And we can solve for various things. Now, the first bit I asked for is how far in does the stomach go? What is X at B? Well, let's make our equations first. I'm getting ahead of myself. So our equations. At A, we have velocity. But X is 0 and Y is 0. So both of these terms go away. At B, our velocity is 0. Our Y is 0, but our X isn't. At C, our velocity is not 0. Our X is 0, but our Y isn't. And so those are my 3 equations for energy. Now I know everything in A. So I'm going, and I want to find X of B. So what I would do to start is say, I know everything in A. So I'll set my energy at A equal to my energy at B. Or 1/2 mVA squared equals 1/2 kxb squared. I can multiply both sides by 2. Divide both sides by k. And square root both sides. Kilograms. VA is 150. Yeah, I had a student, the semester this on exam, I had a student ask me like a complicated One Piece question. And I'm like, hey, someone who knows One Piece? Sure, it's going to be on the exam for all of the students now.
I'm all for the Dark Souls content.
That was a weird one to write because I've never actually played that game. I'm not a big Dark Souls person.
Oh, it's crazy.
A friend of mine gave me the idea for that one. It was only the second time ever I did a question about a game or movie or something that I hadn't played or wasn't familiar with. The other one being the Fortnite question. So, there's my value. I also ask, what's my velocity at C? To get my velocity at C, I will either say EA equals EC, Or I would say EB equals EC. Doesn't matter which one I use. I chose to do EA equals EC because I felt like it. I literally have no better reasoning than that. I guess my M's cancel out. That could be a reasoning. So if I want to solve for VC, I would subtract MGYC from both sides. Divide both sides by M. Multiply both sides by 2. And I'm just going to solve for VC squared again because that's complicated. It is 150 meters per second squared minus 2 times 8 kilograms times 30.4 meters. So VC squared, I don't know what that number is. I don't have that written. Equals something. And VC is the square root of that something, which is 148 meters per second. Sorry, I just didn't, my solutions, I did the square root in one line. You can see I just went straight to, and I'm too lazy to pull out a calculator because no one needs to watch me type in a calculator during class. That being said, go other thing. Yeah, it's been hard to write exams because like so little came out the last year, and especially movies. Like I usually use movies for things, but nothing's come out. So it's been interesting to write exam problems. Anyways, any questions on this? Put my dice away. That's conservation of energy, really. Conservation of energy is just you make an energy equation that is some combination of kinetic, that's what I wanted, some combination of kinetic and potential. Which one of those you need will depend on what the situation is. You're gonna have to look at it and figure it out and figure out where you use each term. But once you have it, you just set everything equal to each other and solve. Sound good? Okay, I'll stop there. Have a good day. I'll see you Monday where we start momentum. See you then.